Okay, thank you very much. So my talk is a general talk about how we can actually use quantum mechanical simulation to aid simulation in biological system. So I come from a slightly different background with respect to the other previous speakers. In a sense, I come from a condensed matter quantum mechanical, mostly density functional theory background. And so for me, when I started looking at some biological systems, the new thing was also to try to do some classical simulation and also some non-sampling method and so on. And I want to highlight some of the challenges that quantum mechanical simulation have when we talk about biological systems, and also because there is not just one quantum mechanical methods and so on. So these are just some biological system that happens to be related to system I've been interested in. So, for example, neuroreceptors, in particular ligand-gated ion channels, and some protein that aggregates related to kidney disease, some photoactive systems. We've heard before rhodopsin, and this is a representation of it. And then I've been interested in polyphenols interacting with proteins, for example, cardiac proteins, or like the polyphenols in green tea, or DNA in plants that are one of the problems that of contamination and of that hinder the extraction of DNA from plants. So that would be interesting because it could bear some information about climate events in the past and so on, given that you can extract the DNA in the same tree for different times. So with respect to what I was used to and I'm still used to when I look at more material science problems, there is a lot of complexity and flexibility in the biological system. That is what makes the application of quantum mechanical methods very difficult. So again, there is an underlying complexity in biological systems that we have all seen. There are very large size scales with respect to what quantum mechanical methods can do, because we can push to a few hundred atoms. Time scale problems, few tens or hundreds of picoseconds with quantum mechanical methods. In many cases, there is a limited structural information, so already starting and building up a system is difficult. And so if we just are going to simulate for a few tens of picoseconds, if already the initial system is not good enough, then it's going to be a problem. They're flexible, they're effect of the environment that is complex and wet and so on. And then we have this quantum mechanical effects. And again, we've heard a lot of more macroscopic quantum mechanical effects. Maybe we're talking here more of what they were defined like trivial quantum mechanical effects, because all these systems are made up by nuclei and electrons, and therefore they satisfy, again, they are subject to the law of quantum mechanics. And in principle, we can write the Schrödinger equation and solve them on a computer, but it's very difficult, and there are a number of challenges. And so what it's when we are interested in looking at biological system at the electronic structure level or at the atomic and molecular level, we just cannot just look at quantum mechanical methods, but we need mixing and matching with different methods. So in particular, molecular dynamics, mostly with force field, also with more approximate methods like coarse-grained method. We need to have input from experiments, at least for the structures. And in many cases, we have to look at and go towards the use of an unsampling method. The one we have been using is metadynamics. We've heard before steered molecular dynamics, that it is another way to accelerate methods, and I just mentioned what it is, and then we might need to use other algorithms like dimensional reduction algorithm and so on. So the quantum mechanical methods and the QMMM methods are one of the methods in a larger kind of toolbox that we need to use. And I always think about as a sort of quality versus price, in a quality versus price framework, in the sense that every choice has a price. So if we want to have a very sophisticated cashmere jumper with respect to a normal wool one, we have to pay more. And so maybe, and this is a little bit what quantum mechanical methods are with respect to, again, doing the molecular dynamics with empirical force field. However, also, and for me, quantum mechanical methods, it's mostly density functional theory. And then from there on, so more post-Hartree Fock methods, again, many-body green function theory that I will mention as a possibility to do excited states. And again, then you can go more sophisticated from quantum Monte Carlo. Again, a little bit the methods that are used in condensed matter. And so we will get accuracy, information on electronic structure, but then there are drawbacks about small scales and short, small size scales and short time scales. And so it's like many times as, you know, having just enough resources, not because we don't have the resources, but because it's, again, impossible to do a very large and long simulation. And so instead maybe to have a jumper, we can just end up with the pair of gloves. However, if this is, I mean, if the purpose is to get our hands warm, and then we can have a coat that is with a less sophisticated kind of material, then like we have in QMMM methods, then we can actually get some meaningful information. But in many other cases, I think we can also get meaningful information simply by doing some classical calculation and then doing the quantum where it's needed. So I mentioned before the metadynamics method. So if we think about a free energy surface, for example, here is simply in one dimension as a function of some reaction coordinates or collective variable, like we call there. If we do just molecular dynamics, the system is going to be trapped in a minimum. And then to go on the other side, it will take a very, very long time and lots of attempts, and so we don't have time to do that. So the idea of metadynamics is that we can discourage the system to revisit the places that it has already visited in the space of that kind of coordinates by adding the history-dependent potential in this space that is built up as a sum of Gaussians that discourages the system to revisit places it has already visited. And when everything has been sampled, basically the sum of the Gaussian will give a cast of the underlying free energy landscape. And this has been a very powerful technique, both used in material science, in chemistry, also in biological simulation to, again, sample free energies and study transition. So the question is that I wanted to pose, and okay, we have already seen many simulations and many applications of that, so the answer is, of course, is yes. So what is, and is there an aid role for quantum mechanical methods in biomolecular simulation, and what are the challenges and what can we do for them? And I just want to start with a very small system that we have been studying, thinking that was very easy anyway, and just an amino acid, aspartic acid. Just as an example that even for these very small systems, there are a lot of degrees of freedom. And so if you want to sample all the rotational possibility and the conformers, the stable conformers that these amino acids have, and there can be, I have a colleague at King's that measure this kind of thing with rotational spectroscopy, then is already a very challenging problems that cannot be solved by quantum mechanical methods alone. And so what we can do, however, is to sample the free energy with force field and with the metadynamics method as a function of all these rotational degrees of freedom. And then this is just a representation where we use a dimensional reduction algorithm called SketchMap. It doesn't particularly matter to represent the multi-dimensional free energy in 2 dimensions. And we can see that, again, the free energy is a little bit like if you have been in London, the Royal Albert Hall, that has all these tiers of seats, and the lowest one are interconnected, and they are the lowest energy conformers, and then there are tiers with higher energy and so on. So we can actually identify the various conformer with that, and then we can refine the calculation with by just doing standard free energy calculation of the various conformers. But again, we can use different quantum mechanical methods. We can use a density functional theory method. This is with the standard bit-leap kind of exchange and correlation. We can do a little bit more correlated calculation like MP2. But again, there is not a complete consensus because in the ranking, because again, different methods have different strength, and and we still do not have, for example, the kind of entropic contribution that we can actually have with the force field methodology at finite temperature. So again, we can use different, we can support with different ab initio method, but there still are some, again, inconsistency that would be nice instead to have once we are able to study fully ab initio with a method that is able to really capture the quantum mechanics of the system. Again, all the methods, if you want, give qualitatively good results, but if we just use these, we're not taking fully into account the anharmonicity of the methods. If we just use the force field, then there are some inconsistency in some description of the hydrogen bond strength and so on. Of course, as we saw before, if we want to study processes in which we have proton transfer, for example, this is a very simple reaction where we have, again, a Zwitter ionic system that would not be stable in water, in the gas phase, and so we would see a proton transfer, or the opposite in water. If we put a neutral aspartic acid in water, then it would actually prefer to be in the Zwitter ionic phase. And so this kind of processes cannot be seen completely with the force field. So again, I think there's still some work to do in bridging what we can do with force field and an unsampling method and so on, and what we can do with the ab initio methodologies. But one of the role that quantum mechanical method can have is in improving the force field. And these are just some examples. It's the same calculation I've done before that was done with the charm force field with 2 other very popular force field. And basically, qualitatively, the information is similar for these b-dimensional free energy surfaces, in the sense that qualitatively we still have the same kind of, okay, there's a cutoff of energy. And so basically where there is nothing is because in this other force field the energy is too high. Is too high. So qualitatively there is a similar information, but from the quantitative point of view, again, there are differences in barriers and so on. And so the quantum mechanical information could be very useful to fit accurate force field. And in condensed matter, there's a lot of work going on at the moment in, for example, using neural network and machine learning kind of algorithm to fit and produce a force field that have an accurate, that are as accurate as the ab initio simulation that they're trained on. In the case of, okay, a piece of silicon is one thing, even in different phases, a flexible protein is another, and I think there could be much more challenges in using, in developing force field with that kind of new generation of methodologies for biological systems. So another kind of system I've been interested in for some time are pentamenically gangated ion channels, and these are very complicated systems. They are ion channels. They are activated by the binding of neurotransmitter, and I've heard this morning that the neurotransmitter may be released as a, in consequence of some interaction with the Potsner molecules. And so these this neurotransmitter would bind 1, 2, 3, we don't know exactly, at the interface between subunits and trigger a series of chemical structural conformational changes that would culminate into the opening of the channel, and then the ion can pass through, and the information between neurons can be transmitted. So they're very important systems, but they're also very, very complicated. And because the structural information is quite limited, then it's not, we don't know exactly how they work at the molecular level. And so we have actually done, a series of calculations, for example, to look at the binding of the neurotransmitter to the extracellular domain of this system. And also here, okay, this is just a portion of the whole system that is much bigger than this. And also with this, we actually use metadynamics to bias the binding and with this particular funnel potential to bias the binding of the neurotransmitter from the solvent in and then in such a way that it could explore the binding site and then out and in and out and in and out. And we use this funnel potential to restrain a little bit the sampling of the solvent outside, because otherwise it would be impossible, and then it can be actually corrected and so on. And so we can actually, again, study various things like the mechanism of binding, what happens, which amino acid they would bind to, and so on. This is GABA, which is Zwitter ionic, so it has a negative and a positive part, and then finally would position itself. Obviously, this kind of simulation would be impossible to do from the point of view of the quantum mechanical simulation, and in this particular case, maybe it's not even necessary, because anyway, there's a lot of electrostatic going on, and we have our neurotransmitter that would bind in between an arginine and a glutamic acid, mediated or not by water molecule and so on. And this is our free energy within the funnel, so we bias the position along the funnel and these other axes along the funnel. And then in the wild type, we find a bound state and a pre-bound state, and we can see also in the projection of the free energy along the funnel. And if we mutate, as experimental did, with alanine, the glutamic acid, or arginine with alanine, then the free energy of binding is disrupted, and so the system is not bounded any longer, and we can see here that there are no minima any longer. But these are sort of microsecond simulations for hundreds of thousands of atoms that cannot be done from the point of view of even density functional theory method. However, if we want to study other things, like what happens if we, like the experimentalists do, if we mutate some particular amino acid with mutation that disrupt the electronic structure. For example, this is a tyrosine, and we have here the aromatic ring, and we want to disrupt the aromaticity. Then we can actually do some, for example, here are density functional simulations in which we can study, for example, what happens if the ring is fluorinated with just 1, 3, 5 fluorine instead of the various group, and actually then study smaller molecules, smaller system, a smaller model of the binding site, and get this kind of effect. So we studied this to look at the effect of progressive fluorination and mutation in disrupting cation-pi interaction in a different receptor, actually, that bind the neurotransmitter serotonin. And these are some other examples where we study again with the smaller molecule the effect of progressive fluorination in hydrogen bond, in weakening the hydrogen bonds, and then try to connect with experimental results that actually mutate in the same way. So these are just some other calculation where we can actually support the interpretation of experiments with quantum mechanical simulation. So a system that need quantum mechanics to be understood, as we saw again this morning and also yesterday, are biological systems. And so in this case, the time scales are small, because we are talking about, for example, for isomerization of rhodopsin, or this is the photoactive yellow protein, and GFP that has also been mentioned, of hundreds of femtoseconds, maybe picoseconds, so very short time scale. But there are other kind of challenges for excited states, because density functional theory, which is the quantum mechanical method that has perhaps the best ratio between computational cost and accuracy, is fundamentally a ground state methodology. And so if we have to go to excited states, then there are approximation and other problems that we need to see. So I've been working with various methods, starting from density functional theory, mostly to test how they can work. So we work with the restricted open shell concham theory, which is a method that is good to study HOMO-LUMO kind of excitation, but is very quick and is very useful to do dynamics in the cases in which it works. We work with time-dependent density functional theory, that again is another method that is becoming very powerful, and we can study system up to 500 atoms or so, but it has problems with respect to some charge transfer excitation, and some of the biological systems have charge transfer excitation. We have also tested another methodology that is very popular in condensed matter, that is the GW and Bethe-Salpeter equation. The GW method is useful to get accurate orbitals, and then the Bethe-Salpeter equation is to study exciton. But exciton in the case of these systems, and we're not talking about exciton from one part of the biomolecule to the other, are quite confined because it's a very small system. So if we think about charge transfer kind of excitation, we have a sort of charge separation also inside the molecules. And so, again, there is an analogy with what in condensed matter can be exciton, but we need to look at particular approximation that work and doesn't work, and so on. I will show you anyway in the next slide some results for that. So again, we also did some QMMM calculation, in particular for the photoactive yellow protein, that is a protein related to the negative phototaxis in some particular bacteria. And what we look at was these are calculations done with time-dependent density functional theory, and we tested the various recipes and so on. We study both the chemical shift, so when the chromophore p-coumaric acid is in the protein, so again is deprotonated, and it builds up some linkage and so on, and then the effect of the protein with the QMMM methodology. These are done actually with the QMMM from the CPMD code, and what we find out, for example, in this particular case, is that in the absorption, the protein shift is the contribution of the protein in the absorption shift is actually quite small, but the protein basically shield the chromophore from the solvent and prevent. And the other significant thing is that it prevents. There is a competition for this particular chromophore between electron detection and electron excitation. And so in the gas phase, again, the two processes have more or less the same energy, but inside the protein again shield the system and protect with respect to electron detachment and the radical formation. And so, again, is there the protein for a role? I mentioned before this other methodology, the GW plus Bethe-Salpeter equation. We wanted to test how it works for biological chromophores with the GW that would take into account beta orbitals. It's actually used a lot in condensed matter to get better band gaps with respect to the usual density functional theory. And we got actually quite good results, and so this has been a first attempt to use these methods. Now, the drawbacks, obviously, of these methods is that they're still not conventional to calculate forces. So they're mostly used for, again, kind of absorption spectrum or spectroscopy, but not yet to do molecular dynamics. That is what, again, we are mostly interested in, especially if you want to study isomerization processes and other problems like that. And at the moment, we are looking at different kind of probes to study these particular molecular rotors that are useful to study the viscosity. They have a part that rotates, and they're useful to study the viscosity of biological system and for bioimaging. And so even to study something as small as this, we have to find a method that would allow describe excitation properly and would allow to do dynamics and then to be put complicated environment, like it could be the one of a membrane or and similar. So the last system I just wanted to mention is that we've been interested in polyphenols, in particular the one of green tea that are supposed to be good for various for various disease, perhaps for everything. And there have been some information about the interaction of these particular polyphenols with a cardiac protein coming from NMR spectroscopy. So we did study the various interaction and came up with some ideas that they can help regulating heart contraction. But this kind of system that can be found again in anti-wrinkle cream are also antioxidant. And this is another of these processes that would need quantum mechanics and it's quite difficult to study. And we can have different kind of, and when we have unpaired electron, that's also when some methodology and density functional theory in the sort of standard way is one, has some issues and problems and to describe things perfectly. So anytime we have, again, unpaired electrons, or we have to do proton transfer, electron transfer, there are additional challenges to be taken in. So it's not just, the message I wanted to give is that it's not just the size of the protein, of the biological system, and the time scale and so on, but it's also the kind of problems and reaction that we are interested in. So I just want to wrap up. So this was just some highlights of how we use quantum mechanical methods to support some simulations and some of the simulation that we have done in biological system. So biological systems are still too complex to be treated fully by quantum mechanical methods. Of course, it depends on which quantum mechanical methods. If we go to more semi-empirical methodology and so on, if you again go towards more and more approximated method, then we can do larger system, but we have to live with the kind of approximation that we have. And all the quantum mechanical methods have some limitation because, again, one has to pay a price. If we go for very, very sophisticated one, then we can only do small systems, and we cannot do molecular dynamics, we cannot do metadynamics, and unsampling, and so on. If we go for more approximate one, we can make mistakes. And in particular in the excited states simulation, in the electron transfer and so on, we need to be careful. So we have various challenges, the size, the conformational complexity, the time scale, the accuracy, but there are a lot of new method development that are going on, from the development of more accurate force field to various methodology to improve the methods. Again, someone has spoken about electron-phonon interaction today. There's a lot of development also in condensed matter, so I think it would be nice for different community also to share methods and progresses. Of course, quantum mechanical methods are necessary for a number of processes like chemical reaction, electron transfer, excitation, as I said before, also to get good optical and vibrational spectra that can be compared with experiments. And so we have to go for some practical solution, either like we've seen before, using QMMM methods, different level of quantum mechanical calculation depending on the problem that we can solve and that are suitable for, and then understand what is useful to experimentalists as well. And I just wanted to conclude with a quote from Schrödinger. So we have seen before the first part, but there's also another bit in the book that I always like to cite, that it says the obvious inability of present-day physics and chemistry to account for such event is no reason at all for doubting that they cannot be accounted for by those sciences. And we were talking about the event in space and time. So there's a lot that is done, and there's a lot that can be done with simulations. Not all can be done at the moment for various limitation of the methods and of the complexity of the system, but I think there is a lot of progress that is going on, and so a lot of possibility for the future. And I just want to acknowledge various people, various students in my group that have contributed over time to the calculation that I show, my experimental collaborators and some other collaborators. Thank you very much.
Lots of interesting systems. I have a curiosity. When you do the yellow fluorescence protein, doesn't the chromophore change shape when you have an excitation, or stay rigid?
No, it isomerizes.
And how do you do that? You do the
so
excitation?
we didn't actually do the full isomerization in that particular things. I mean, either you forces. This was just we just studied the excitation and the absorption spectrum.
And is the time scale, just out of curiosity, is the absorption time scale different than isomerization? You have to do both together, or can you do as two separate events?
No, it can be done in principle. The problem that we had when we did the calculation is, so for the isomerization, then you need to calculate the forces. You need some method that would accurately reproduce the potential energy in the excited states, maybe also some non-adiabatic dynamics and so on.
That's what I'm curious.
So we just didn't do
you need
this.
non-adiabatic dynamics or not? That's what I was curious to know. Or if you can.
Probably yes for this. I mean, it might be not that different from rhodopsin. Yeah, and these are done with time-dependent density functional theory that have produced they still have some barriers. So to do the dynamics in these excited states, you probably need something more like, I suppose, CAS-SCF or CAS-PT2 or these more standard things. So what we did was instead a study with time-dependent DFT, and then with the other one, yeah.
I wondered if you could comment on tackling something like the photosynthetic reaction center. How you could manage to compute charge transfer states and.
There are some work that has been done. I mean, the charge transfer state with time-dependent. So time-dependent density functional theory depends a lot on the system. So in some system it works, and some system it doesn't. Probably for this kind of system, other kind of technique like CAS-PT2 and so on can be more suitable, but they're also more expensive. So, yes, I've never actually done it myself. But there's quite a lot of work also in photosynthesis done for bit and pieces, and there are also some work done at the density functional theory level.